Hello everyone and welcome to General Chemistry 2, lecture number 18. In my course, this is the final lecture in unit number 3. This one is on solubility equilibrium and KSP, and this covers OpenStax section 15.1. Alright, so first, a quick discussion here. In General Chemistry 1, you probably learned about some solubility rules, and while these are generally accurate, they were pretty vastly oversimplified. Even some nearly insoluble ionic compounds will actually dissociate weakly, and yes, unfortunately, I'm sure you're probably sick of them by now, but this does involve more ice tables. So let's look at what's going on here. Suppose we've got a compound like silver chloride, which according to the solubility rules is insoluble. The truth, it's partially soluble. Now, it's going to be very smallly soluble, and we'll calculate this. But what's happening here is the solid AgCl is partially dissociating into the Ag plus and Cl minus ions. So here, this shows the solid AgCl surrounded by water molecules, and so since it only partially dissociates, maybe a couple silver and chloride ions break off here and dissolve in water, but the rest of them stay together. So because AgCl is only sparingly soluble, the equilibrium concentration of the Ag plus and the Cl minus will both be very low. So since this is an equilibrium reaction, we can write an equilibrium constants. These are referred to as KSP. These are called solubility product constants, which is what the SP stands for. So KSP would be equal to the concentration of Ag plus times the concentration of Cl minus. So the two products. Note that the AgCl is not included in this expression or this equation because it is a solid. So this is an equilibrium that exists between a slightly soluble salt and its dissociated ions. Oh, and I just answered this question right here. Second question, are KSP values likely to be large or small? You should recognize that these values are likely to be small, since most of the solids we're going to be working with are those that we were taught were insoluble, which means in this case, they are actually just partially dissociated. Anything that is considered to be soluble, like sodium chloride, for example, it completely dissociates into its ions, and so it would just be a forward-only arrow instead of using this double, reversible equilibrium arrow. Another example of one of these reactions would be the dissociation of calcium phosphate. And remember that with ionic compounds, when you turn the compound into its ions, any subscripts become coefficients. So Ca3 PO42 would give 3 Ca2 plus and 2 PO43 minus. So when you set up the KSP expression, remember that those coefficients then become exponents. So this would be Ca2 plus to the third power, PO43 minus to the second power. Here is a list of various KSP expressions. Now in my course, and really, I would think most chemistry courses, you're not going to be asked to memorize these. They will be given as needed in the problem, or you may be asked to calculate them, but I just want to note them here. There is a bit of a wide range. There are some that are pretty high, like a 10 to the negative fourth, a 10 to the negative sixth, but for the most part, you can see that these values are generally very small, indicating that these ionic compounds, calling them insoluble, is not accurate, but it's not completely wrong either. Many of them are only very partially soluble. All right, so let's try a practice question here. What is the solubility of silver chloride in grams per liter? So what we're going to do here is we're going to start with the KSP of the compound, which is given as 1.6 times 10 to the negative 10th. Then we're going to write out our dissociation reaction, which in this case would be AgCl forming Ag plus and Cl minus. We're going to use an ice table to establish the concentrations of cations and anions. This will give us the molar solubility of the compound, and then finally we can find that solubility in grams per liter. All right, so we'll set up our ice table. We've got whatever the initial molarity of AgCl is. The Ag plus and the Cl minus are both 0. Our changes will be minus x and plus x for both of these. And then our equilibrium concentrations, we're just going to call it M minus X For the ions, it's X for both. Note that I'm calling this M minus X. Since this is a solid, whatever its concentration is doesn't really matter. This is just going to get X'd out, and it's not going to get included in the KSP expression. So KSP here would be equal to the concentration of Ag plus times the concentration of Cl minus. Again, the AgCl is not being included because it's a solid. So KSP, in this case, is equal to X times X. So this is X squared is equal to 1.6 times 10 to the negative 10th, which gives an X value of 1.265 times 10 to the negative 5th. Now, it's important to note here that this value right here, whatever you find X to be, whatever X is equal to, this is the molar solubility of the compound. We will see examples of problems where you might have, 3Ca2 plus and 2PO4 minus, for example. The concentrations of the ions is not the molar solubility. Whatever the X value is the molar solubility of the compound. Basically, that's how much of the solid dissolves in moles. So again, one more time, if you are asked for the molar solubility of the compound, whatever you find X to be is your answer. X is the molar solubility of the compound. Now, in this problem, it just so happens that X is equal to the Ag plus and the Cl minus, so this tells us the concentrations of the cations and the anions. And again, noting that our X value gives us the molar solubility. So then our final step to find the solubility in grams per liter, we'll take that 1.265 times 10 to the negative 5th moles of AgCl. That dissolves per 1 liter of solution. And we will just go ahead and convert from moles to grams using the molar mass of silver chloride, since it was looking for the molar solubility in grams per liter. So 1 mole AgCl on bottom, 143.32 grams of AgCl on top. And this gives a solubility of 1.81 times 10 to the negative 3rd grams per liter. And this is the final answer to this problem. All right, let's go ahead and look at another problem. This one states the KSP of PbI2 is 1.4 times 10 to the negative 8th. How many grams of PbI2 will dissolve in 1 liter of water? Essentially, what is the solubility in grams per liter? So let's start by writing the dissociation reaction. So PbI2 dissociates to form Pb2 plus and 2I minus. Then we're going to set up an ice table. So PbI2 using that reaction, PbI2 forms Pb2 plus and 2I minus. We'll set up our ice table. Again, we can just use a generic concentration of M for the solid because it doesn't matter what its concentration is. It's not going to end up in the K expression anyways. Importantly, we start with 0 for both our products, 0 for Pb2 plus and 0 for I minus. Our changes here, it's minus X for the solid. It's always going to be minus X for the solid. The solid's always going to have a coefficient of 1. Plus X for Pb2 plus and plus 2X for the I minus. Again, remembering that the change is based on the coefficient. We get equilibrium concentrations of X and 2X respectively for our 2 ions. Now we can write our KSP expression excluding the solids. So the solids can go ahead, you can go ahead and wipe that out. Oh, sorry about this. I know I'm moving a little quickly. My animations could have been a little bit better here. So ignoring the PbI2, ignoring the solid, KSP is equal to the concentration of Pb2 plus times the concentration of I minus squared, remembering that that coefficient also becomes an exponent. So KSP is equal to X times 2X squared, and note the 2X goes inside the parentheses. So this means essentially that KSP is equal to 4X cubed, since that 2X squared is equal to 4X squared. So X times 4X squared gives 4X cubed. And our KSP value given was 1.4 times 10 to the negative 8th. So we can say that 4X cubed equals 1.4 times 10 to the negative 8th. We can solve for X. We get X equal to 1.518 times 10 to the negative 3rd. Remember that this is the molar solubility. This is how many moles per liter of PbI2 will dissolve. The question is asking for the answer in grams per liter. So we can take that X value, 1.518 times 10 to the negative third. This is the molar solubility, so moles PbI2 over 1 liter. And we can convert from moles to grams using the molar mass of PbI2, which is around 461.01 grams, giving us a final answer of 0.70 grams per liter. All right, let's look at another practice problem. This one states the solubility of nickel phosphate is 7.796 times 10 to the negative fifth grams per liter. What is the KSP? Now we're working in the reverse direction. So we are again going to start by writing out the dissociation reaction. So Ni3PO4 solid forms 3 Ni2 plus and 2 PO4 3 minus. Then we're going to convert that solubility from grams per liter to moles per liter. So 7.796 times 10 to the negative fifth grams nickel phosphate. Convert that to moles using nickel phosphate's molar mass. And I find that we get a molar solubility of 2.13 times 10 to the negative seventh moles per liter. Next, we're going to use stoichiometry to determine the concentration of nickel and phosphate. So our starting amounts are 0. Our change, remember it would be, so we're sort of doing an ice table here. Remember, also, sorry, I'm going to back up a little bit here. Remember, this is the molar solubility, and the molar solubility is X. So if we're thinking about this in terms of an ice table, our changes would be minus X for the solid, plus 3X for nickel, and plus 2X for phosphate. So minus 2.13 times 10 to the negative seventh for the solid, plus 3 times the 2.13 times 10 to the negative seventh for nickel, and plus 2 times 2.13 times 10 to the negative seventh for the phosphate. This gives a nickel ion concentration of 6.39 times 10 to the negative seventh, and a phosphate ion concentration of 4.26 times 10 to the negative seventh. Finally, what we can do here is write the expression for KSP and plug these values in. So we find that, sorry about that, there should be a line on the bottom here. The solid gets excluded, so there should be a little line right here. Hold on, let me pause the video. Okay, sorry about that, I've got that fixed. So again, note that we're ignoring the solid on the bottom. So our KSP expression would be the concentration of nickel 2 plus to the third power times the concentration of phosphate to the second power. So we can take those concentrations we found, plug them in. So the KSP would be equal to 6.39 times 10 to the negative seventh cubed times 4.26 times 10 to the negative seventh squared. And we get 4.74 times 10 to the negative 32nd. And so this is our KSP value. So this is how we can work these problems in reverse. Again, I'm going to emphasize, this is the fourth or fifth time I've said this, but it's extremely important that you remember that the molar solubility is equal to the X value. So in the previous two problems, when you were asked to find the solubility, you needed to solve for X. X gives you the molar solubility, and then you can convert to grams as needed using a molar mass. Here, you're asked to find the KSP. You're given the solubility, so you can work backwards to find moles per liter. That tells you your X value. Once you've got the X value, you can solve for these ion concentrations and then plug them in for KSP to solve. All right, now we're going to recall Q, the reaction quotient. We're going to use Q by comparing it to KSP to evaluate a solution. So remember, comparing Q to K tells us which direction the reaction is going to proceed. So if we find that Q is less than K, this means we have an unsaturated solution. The reaction is going to proceed to the right towards the ions, which means no precipitate will form. So we're going to use this to predict precipitation. And remember, precipitate just means solid. If you find that Q is equal to K, this means we have a saturated solution, so there shouldn't be any precipitate. If you find that Q is greater than K, this means you have a supersaturated solution. Remember that if Q is greater than K, the reaction proceeds towards the left. And if the reaction proceeds towards the left in these solubility equilibria problems, that means we're going back towards the solid, and so a solid forms, or more specifically, a precipitate will form. Let's look at an example problem. If 2 milliliters of 0.20 molar NaOH are added to 1 liter of 0.10 molar calcium chloride, will a precipitate form? Note that the K value given for calcium hydroxide is 8.0 times 10 to the negative 6. So since we're being asked if a precipitate will form, we need to calculate the value of Q and compare it to the given value of KSP. So start by writing the dissociation reaction of calcium hydroxide related to that KSP given. So CaOH2 forms Ca2 plus 2OH minus. So our Q expression here would be simply Ca2 plus, the concentration of Ca2 plus, times the concentration of OH minus squared. Next, what you can do is use the given volumes and concentrations to determine the concentration of the Ca2 plus and the OH minus. So we've got 2 milliliters of sodium hydroxide and 1 liter of calcium chloride. So starting with that sodium hydroxide, I've got 2 milliliters. I'm going to convert that to liters, then multiply by the given concentration, and then finally multiply by the ratio. The ratio here I'm noting is that there's 1 mole of hydroxide per every 1 mole of sodium hydroxide. This tells me that I have 4.0 times 10 to the negative 4th moles of hydroxide present. Next, I'll do the same for the calcium chloride. I've got 1 liter present, so I don't need to do the milliliter to liter conversion. I can just go ahead and multiply by the given concentration of 0.10 moles per 1 liter. And then finally, converting from calcium chloride to just calcium, again noting that it's a 1-to-1 ratio. This tells me that I have 0.10 moles of calcium ions. I am going to want to calculate those new concentrations. So I should note here that my total volume, it would be the 2 milliliters of the sodium hydroxide plus the 1,000 milliliters of calcium chloride, giving me a new volume of 1,002 milliliters or 1.002 liters. With this, I can calculate my concentrations. So my OH minus concentration, that's the mole value I found on the previous slide, 4.0 times 10 to the negative 4th, divided by the new volume, giving me a concentration of 3.992 times 10 to the negative 4th molar. I'll do the same for the calcium ions, the 0.10 moles divided by the 1.002 liters, giving a concentration of 0.0998 molar. Finally, we can plug these into our Q expression. So again, remembering the solid on the bottom is ignored. Our calcium ion concentration is 0.998. Our hydroxide ion concentration is 3.992 times 10 to the negative 4th. Don't forget to square the hydroxide ion concentration. This gives you a Q value of 1.59 times 10 to the negative 8th. Because Q is less than K, this means the reaction is going to shift to the right to form more products. Since you are shifting towards the side with the dissolved ions, a precipitate will not form. And so that would be the final answer to this question here. All right. Now we're going to look at a similar problem. This is an analytical technique called selective precipitation. This question asks, what concentration of Ag plus is required to precipitate only AgBr in a solution that contains both Br minus and Cl minus at a concentration of 0.02 molar each? Okay, so our strategy here is to note that each compound will form a precipitate only when Q is greater than K. So what we want to do here is we want to precipitate only the AgBr. We only want to precipitate this compound with the smaller KSP value. So what we want here is we want a concentration of silver ions that is big enough where the Q is greater than the K for AgBr to force this reaction left and precipitate the AgBr, but not so high that it forces this reaction back to the left. So what we're going to do is we're going to start by setting up an ice table to figure out what Ag plus should be in each case. We're going to start with the first reaction, given the reaction with the smaller K value, the AgBr dissociating to form the silver and bromide ions, whose KSP is 7.7 times 10 to the negative 13th. We set up our ice table. This time, I'm just going to go ahead and X out the AgBr. We don't care about it. Our initial concentration of silver is 0. Our initial concentration of Br minus, note here, is 0.020. Our changes are still going to be plus X for each, giving equilibrium concentrations of X and 0.020 plus X. We can go ahead and set up that KSP expression. KSP is equal to the concentration of Ag plus times the concentration of Br minus, remembering that the solid does not appear in the denominator. This is equal to 7.7 times 10 to the negative 13th. We can plug these values in for Ag and Br. KSP is extremely small here, so we can ignore that X. We can use the small x approximation, and we can solve and find that X is equal to 3.85 times 10 to the negative 11th. This tells us our Ag plus ion concentration at equilibrium. So when the reaction is at equilibrium, this is your Ag plus ion concentration. So if you wanted to force this reaction back left, if you wanted to precipitate the AgBr, you would need to have a silver ion concentration that is greater than 3.85 times 10 to the negative 11th. That would mean you have too many products, the reaction would shift left, and the precipitate would form. All right, now second portion of the question, we're going to work through this math for AgCl, the value that had the larger KSP. So AgCl dissociates into the silver ions and the chloride ions. We're still starting with 0 of the silver ions, but we are also starting, sorry, the wrong thing is highlighted here. We're also starting with the 0.020 molar of Cl minus. Our changes are still plus X for both, giving us an equilibrium concentration of X and 0.020 plus X. We can set up our KSP expression. KSP is equal to the concentration of Ag plus times the concentration of Cl minus. This is equal to the KSP that was given, 1.6 times 10 to the negative 10th. These values can be plugged in here, and we can once again use the small x approximation, and we can go ahead and solve, and we find that x is equal to 8.00 times 10 to the negative 9th. This is our silver ion concentration at equilibrium for this solubility equilibrium. So what this means then is if we don't want the silver chloride to precipitate, our Ag plus ion concentration needs to be less than this. So the final answer to this question is then you would want the silver ion concentration to be greater than 3.85 times 10 to the negative 11th. This would allow us to precipitate the AgBr, but it needs to be less than 8.00 times 10 to the negative 9th. Because again, note that the problem asks what concentration is required to precipitate only AgBr. So your answer would be the Ag concentration needs to be greater than this, but less than this. Okay, here's a brief think and discuss question. You have a solution that contains 0.050 molar of calcium ions and magnesium ions. If you add aqueous hydroxide to this solution, which will precipitate first? Calcium hydroxide or magnesium hydroxide? I do want to note that you don't need to do any math on this problem. Just think about the reactions given here and see if you can come up with the correct answer. So please go ahead and pause the video, think about this one for a moment. All right. Oh, sorry about that. I thought I had the answer given on the slide. So the correct answer here is the magnesium hydroxide would precipitate first. Why? Because it has the smaller KSP value. So because it has the smaller KSP value, the Q value will become greater than the K value more quickly. When Q is greater than K, reaction shifts left. Reaction shifting left here results in the solid forming or the precipitate forming. So if asked a question like this, the compound with the smaller KSP value will always precipitate first. Okay, We've got just a couple more problems to look at. Here we're going to look at the common ion effect and solubility. The presence of a common ion decreases the solubility of the salt. Why? This is related sort of to what we learned about 2 lectures ago with buffers and also related to Le Chatelier's principle. Let's work through some calculations here and see how this works out. This question states, what is the molar solubility of AgBr, first in pure water and second in a solution of 0.0010 molar NaBr? Let's start with letter A. So I can go ahead and set up my ice table. I'm ignoring the solid. The initial concentration of the both ions is 0. Their changes are both plus X, giving equilibrium concentrations of X. Remember that X tells you the molar solubility. My KSP expression would just be Ag plus times Br minus. So this would be X squared is equal to 7.7 times 10 to the negative 13th. And for X, I get 8.8 times 10 to the negative 7th. So this tells you the molar solubility. This means 8.8 times 10 to the negative 7th moles of AgBr would dissolve per liter of water. So this answers question A. Let's move to question B. What is the molar solubility in 0.0010 molar NaBr? So I can again set up an ice table, ignore the solid. Initial concentration of silver is 0. Initial concentration of Br minus is 0.0010. Their change for both is still plus X, given equilibrium concentrations of X and 0.0010 plus X. Remembering that again, X is still molar solubility. KSP is equal to Ag plus times Br minus, which is X times 0.0010 plus X. We can actually use the small x approximation here. Sorry, let me pause real quick and fix my slide. Okay, sorry about that. Yes, because this k value is so small, we're using small x approximation. So x would just be the k value divided by this concentration, and you get x is equal to 7.7 times 10 to the negative 10th. This is how many moles of AgBr would dissolve per liter of the 0.0010 molar NaBr. Note now that the solubility decreased. Why is this? Again, think about Le Chatelier's principle. If we had 0 of both of these ions at the start, then our reaction is going to shift fairly strongly to the right, which results in more ions being produced, a higher or a greater molar solubility. If you got some of one of the ions present, the reaction is just not going to shift as strongly to the right, and the molar solubility decreases. All right, last type of problem to look at. This is on pH and solubility. So insoluble bases dissolve best in acidic solutions, and on the flip side, insoluble acids dissolve in basic solutions. You may be given a problem like this where you're asked, what is the pH of magnesium hydroxide in aqueous solution if the KSP of MgOH2 is 1.2 times 10 to the negative 11th? You may also be asked a question like, how would increasing the pH, basically increasing the hydroxide ion concentration, affect the solubility of MgOH2? Let's go ahead and take a look at this first problem. So what's the pH of MgOH2 in an aqueous solution if the KSP of MgOH2 is 1.2 times 10 to the negative 11th? This is essentially another ice table problem, just like we've been looking at before. So you can write out your dissociation reaction. MgOH2 dissociates reversibly to form Mg2+ and 2OH-. Ignore the solid. Initial concentrations of 0 for both of the products. Our change values should be plus X for magnesium and plus 2X for OH-, given equilibrium values of X and 2X respectively. Then you can set up your KSP expression. KSP is equal to the concentration of Mg2+ times the concentration of OH- squared. This is equal to X times 2X squared. Note that again the 2X goes inside the parentheses. So we can say then that our KSP value, 1.2 times 10 to the negative 11th, is equal to 4x cubed. This gives an x value of 1.44 times 10 to the negative 4th. Note that this question is not asking for the molar solubility. If it did, this would be the answer. This question is asking for the pH. So we should use that x value to solve for the hydroxide ion concentration. Here we established that OH minus is equal to 2x, so OH minus would be 2 times this value, which gives 2.88 times 10 to the negative fourth. Now we can solve for the pOH. So the pOH is the negative log of the OH minus concentration. So if you take the negative log of this value, you find that the pOH is 3.54. And then remember that to find the pH, you would just take 14 minus this value. And our final answer, the pH is equal to 10.46. Second question, how would increasing the pH, or essentially increasing the OH minus concentration, affect the solubility of MgOH2? Note here that since our pH is 10.4, our starting pH is 10.46, if we add more OH minus, this is going to increase the pH. The hydroxide here is a common ion, and as we just saw previously, what happens when you add a common ion, the solubility is going to decrease based on Le Chatelier's principle, as I mentioned in the previous slides. So if you've got a base dissolving, increasing the pH would decrease the solubility. However, if you were to decrease the pH, this would increase the solubility, and then you would see the inverse relationship if you had an insoluble acid. Okay, so that concludes this lecture. I've got 4 practice problems for you to try right here. So please go ahead and pause the video if you would like and try these practice problems, and then I will reveal the answers on the next slide. Here are the answers. That concludes this lecture, and for my course, that concludes Unit 3. As always, if you've got any questions, please feel free to reach out over email or comment down below. I hope you enjoyed this and found it useful. I'll see you in the next lecture when we start Unit 4, and I hope you have a great day.